Hello everyone, in this video we'll present my work on generative adversarial networks. In this case will be a 3D generative adversarial network that uses finite element computations as a physical surrogate of mechanical properties. This is part of my work during my assistant professor time in Zhejiang University in China. And the application of this is mainly scaffold generation for implantology or similar things in biomedicine. Actually, I'm not an expert on biomedicine. I'm a civil engineer, but I will be doing the numerical simulation of these scaffolds and the synthetic generation using generative adversarial networks in this work. So first of all, let's see what a generative adversarial network is. We see the diagram here in which you have a generator and a discriminator and a database of real samples and fake samples that come from the generator, which is a neural network generator. So this is an adversarial machine learning model in which the target is to develop a generator that is able to generate images that look like the images in the real database. So look, to make images that are similar to the database, it means that the generator will be able to encode features in a latent space that in an unsupervised manner finds from the real images. Okay, and then the discriminator has the role of police, trying to find the fake samples in a pool which contains real and fake samples. So how this works is the generator starts generating fake samples, starting from a seed that comes from a latent space. In this case, the latent space has a dimension of 128. And then we feed a discriminator with real and fake batches of samples, and the discriminator tries to say which one is real, which one is fake. If the discriminator gets it right, it's positively rewarded. If not, it's negatively rewarded. The same for the generator, but the contrary. When the generator is able to fool the discriminator with fake images, it's positively rewarded. So with this, we update the weights and biases of the neural networks that compose the generator and the discriminator. And this continues in an adversarial game that eventually end up with a nice equilibrium. And at that point, we will have a generator that generates images that look like the real images and a discriminator that is able to discriminate the real one from the fake one. Okay, that's fine, and this is used to generate images that are very popular in the internet, like fake celebrities, something like that. But in science, we're interested in the scientific properties of these images. In this case, we're interested in the mechanical properties of this scaffold or this 3D porous material. So how to make sure that what we generate has the same properties as the real samples? Because this is an unsupervised learning model, we have no way to give any quantification of the quality of the generated images. So it means generator and discriminator play an adversarial game. They give a value for the loss function that serves to update weights and gradients, but there is no relative measure to this loss that is related to actual quality of the images, because this loss is only related to the quality between ability between generator and discriminator, but there is no absolute measurement of the quality. So in other words, we have no posterior measurement of quality. Okay, what can we do? We can add an informed discriminator. In this case, you see it in parallel to the neural network discriminator. And in this case, this discriminator will have knowledge about the physical properties of our images. How do we do this? We take the images, which are in 3D, as I said, we segment it, so we separate the void from the solid. we mesh, we run a finite element model, and the finite element model allows us to homogenize the solution and to get the elastic coefficients of the medium. Okay, and then we can run some statistics on these coefficients, and these statistics allow us to run some statistical tests like p-tests. We get some p-values, and this can be used to compute errors and gradients that serve to update the generator. Okay, so hopefully if we run these two in parallel with some kind of averaging of the two or some other rules, we hope that we will end up with a generator that generates images that encode the most significant features of the real image database, plus they reproduce the correct physical properties. In this case, the properties that we computed in this finite element simulation. Okay, so the workflow is, as I said, we segment the images. Here in the A, B, C, D figures, we have a real image in the A, and the other three are synthetic. We mesh them, we run finite element models, and then you see the skyline of a stiffness matrix in void notation. So you know, in 2 dimensions, this needs to have 36 components, but if we make several assumptions like orthogonality of several things, we end up with 9 coefficients to fully define this orthotropic material. And these are the 9 coefficients that we will use to run statistics to decide whether or not the synthetic images are significant, meaning they have the correct mechanical properties or not. So what's the conclusion of this? Well, I jumped some steps here, but actually we run many tests in which we have pure generative adversarial network. So this is the PT, pre-trained state. And from this state, we run several models in which one is still the bare bones generative adversarial network without supervision. And then we have several supervisions, like running different functions of weighting between the physics and the neural network discriminator. So if we run statistics on the different coefficients, we can see the simulations that throw better results. We can see like C1 is quite good because there are several coefficients that are in bold. It means they have higher scores. And we can also look at the void notation using bar plots, which coefficients are better or worse. But concluding, we can say, I will just synthesize most of this data for you. We can say that running the finite element model in parallel to the adversarial training scheme, you get a better reproduction not only of the images in terms of general features, but also you get a good reproduction of the homogenized stiffness coefficients or elastic coefficients, meaning that what we propose here, which is using a discriminator which is based on physics to support machine learning in a 3D generative adversarial model, is feasible, and it actually produces good results. So this is a good alternative to use pure unsupervised machine learning in scientific applications. For instance, in this case, in the generation of scaffold bone images from a computerized tomography. Okay, in the next video I will probably talk about another generative adversarial network, in this case containing a 4-phase material with ice, water, and voids and solid grains. Thanks for watching. Bye.